Greeting, guys. My name is Rajiv Joshi, and I am VP of Industry from CASS Society. And my privilege to uh, introduce or this particular webinar, which CASS has sponsored. We are always looking for good industry folks and participation of industry and CAS. And this is a classic example of this webinar. So our speaker today is Dr. Matt Ziegler, and he's going to enlighten you with all his expertise and his work in the AI related field and also physical design work that he has been doing. Matt Ziegler is a principal research scientist and manager at IBM TJ Watson Research Center, Yorktown Heights. He received his PhD degree in electrical engineering from University of Virginia, Charlotte in 2004. Since joining IBM Research in 2004, he received several technical accomplishment awards in the areas of processor design, design automation, and low power design. Currently, he is manager for VLSI Design Group at IBM Research and, and that developed IBM Spyre AI Accelerator. Previously, he has directly participated in the design of Z Systems, Power Systems, and Blue Gene product families. Dr. Ziegler is also an adjunct professor at Columbia University in Electrical Engineering Department, where he has taught classes in VLSI Physical Design and Logic Design. He is a recipient of 2018 Mehboob Khan Award from the Semiconductor Research Corporation and is a member of IBM Academy of Technology. He has served on various conference committees, including being ISLPD 2019 General Co-Chair, and has organized the IEEE IBM AI Compute Symposia since 2018. So let's welcome Matt. Matt, now the floor is yours.
All right. Thank you, Rajiv. Appreciate the introduction. I appreciate the kind of motivation to get me out here and to hopefully share some interesting thoughts. All right, so get started. So my talk today is going to be managing complexity in advanced VLSI design, physical design. I'll talk about methodology automation, and I think by the laws of current research, I have to put AI in the title too, but I will talk about hopefully some interesting things on that topic as well. So let's get started here. Here's an overview. So I'll start off with talking about the design aspect of VLSI design. Maybe get a little abstract here, but then I'll bring it in and then I'll talk about you know, previous and modern VLSI design methodologies with kind of a focus on some of these semi-custom techniques of a little time past and how they're relevant today. I'll also focus on design flow tuning, and hopefully what I mean by automating the outer regime will be clear once we get there. And then I'll talk about some challenges beyond those topics, things that maybe are maybe not so obvious, but kind of keep you up at night when you're actually doing product scale tape out tasks. So here's my warning. This talk is going to be a little bit of a perspective on design, kind of things I'm rolling around in my head on kind of during the day. It might be a bit of a retrospective prior work. So some of the slides will be older, but also I think they're totally relevant. And I think I probably had more time when I was younger to take nice design screenshots than I do now. So I'll show those and also relate that to how future work will come up. I'll give a little bit of background in case you're new to these topics. And then yeah, hopefully this could be a good mechanism to throw out some ideas and see what sticks. I'm happy to kind of get feedback. I'm kind of thinking about these things now on the fly, so hopefully you find them interesting. So let's get started. Now I mentioned I'll be a little abstract. So what makes VLSI design a design problem? Uh, Basic question, and this is really maybe generally about design. I think it comes down to design being really search, not a closed form computation. So that's how I want to start off. This is really frame it somewhat abstractly to say we're in a not a closed form problem space. We're doing something that is kind of the path is undetermined. You might have a couple steps that are sort of obvious, and then once you sort of get to that blank canvas, that's when in my mind design starts. And you need to come up with a kind of a strategy that's more iterative, things that you have to do trial and error. And also heuristic will come in. And so I think these are a lot of things more philosophically about design, and I think they apply quite well to the VLSI design problem. Now we do have modern automation parallels. I'll just name a couple. Like Bayesian learning is kind of using this concept of observe, update your, uh, let's say, confidence, make new decisions. Reinforcement learning is also doing this, choosing an action, having a long-term goal, kind of working out a strategy. So I'll start with this as kind of the design problem at hand. And I'll compare it against what I think is maybe a more direct calculation. And so in a calculation, we're really performing kind of a fixed, uh, let's say procedure. We kind of know what we want. Uh, we kind of know the path. We're just going to kind of grind out the answer. And a key thing here is the move set and problem are typically fixed. And so you kind of again, you have a fixed problem, you know what you're doing, you can somewhat guarantee success if it runs correctly, if you've implemented the calculation correctly. Design, I think, is a whole nother animal. And so we kind of discover the solution through search. And I'm trying to be a little practical that if you could say, okay, we had infinite compute, infinite time, yeah, you could probably search every possibility, but and maybe write a master algorithm or calculation. But I think practically there is a clear difference that when I talk about the number of degrees of freedom I'll mention, it's not something that we can kind of say is a clear calculation. And so the idea is your path emerges as you go through trial and evaluation. Problems may shift, and even the number of moves may change. And often you're kind of happy when you have something good enough under real constraints. The actual trade-off or ROI of compute time is also a key aspect. Is so when you get something that's good enough, you might go with that. You might invest more time, and you might come up with multiple solutions. So that's really, I think, the heart of design in this case. So here's why VLSI, and there's probably more reasons. Here's the four I could think of. Uh, is a real design problem. It's at the root or the kernel of the uh, design flow. These tools are NP, have NP hard problems to solve. They're extremely compute intensive. These each like step might run days or weeks, uh, and use massive amounts of memory. So each individual, let's say, trial is expensive, uh, computationally. And then you add that to the search space. I would say there's a vast, near infinite number of, uh, let's say, possibilities you could explore. So that makes it quite complicated. Um, and the problem can be non-stationary too. I mean, the idea that the design can change. We have so many changes happening in flight. Specs change, logic bugs, ECOs, technology changes. Oh, you got a new PDK, you have a new IP update, your problem changes. So that's another aspect I think this adds this challenge. And then also the move set is open. The number of moves is not closed. I can come up with new design techniques. Uh, Designers can be creative. So that's kind of an interesting thing too, is the number of possibilities in your search is changing and the environment's changing and it's very complex. So that's the challenge we're dealing with. But you know what? We've been designing chips for a while, so we do have a somewhat of a handle on it. And This is just a maybe an abstract. You could draw this many different ways, this picture, but this is an example of what you might do in a design process. There might be some kind of common steps to start off that are more like calculations, and then you sort of move into it could be from a human perspective more of like a trial and error, maybe not so precisely defined process, and you might try multiple attempts in parallel. Some may hit dead ends, and you might then wind up with multiple solutions. And then the question is, as you get these solutions, you would evaluate, are any of these good enough? And if so, do I want to invest more time to get a better solution, or do I want to take this and go with it? So this is, in my mind, the at least this is what I go through sort of in a non-structured way when I do design. So a quick comparison to kind of finish up some of these aspects is that if I would compare this to another search problem like chess, the big difference I would say are, is the complexity, but kind of breaking it down. I mean, chess is a complicated game, but computers are really good at it. We can write, for years. And so it is a finite solution space, a well-defined problem. You can throw compute at it and do a pretty good job. There's, a fixed set of, the game is sort of, not changing. I mean, you have a chessboard and a number of pieces. They don't change their ability to move mid-game. So it's like a really stable known search problem. And in design, I think, all the other aspects, all these comparisons are kind of different. I mean, it's again, I mentioned MP hard at the kernel calculation. Things change. The space is complex. The moves are open-ended, and the net effect is I think you have a search problem, which is a problem that's potentially reframing within a potentially expanding search space. So that makes it quite challenging, also quite interesting, which is why we'll talk about this today. So I'm going to now try to get a little bit less abstract, but hopefully I've convinced you that uh, the design problem is challenging and complex and interesting. Uh, so now in terms of the design space, how do we navigate it? And I mentioned there's a near infinite number of moves with expandable degrees of freedom or design moves. I kind of use those terms interchangeably here. And then selecting a good move can be very efficient. If you do the right move, you can make significant progress. But the number of moves here is that's one of the I would say complexities here is that there's so many things you can do. What exactly should you do? But fortunately, if we're talking from a human perspective, we develop heuristics, experience, intuition, and these guide us through that process. And so this helps us navigate. You hopefully get better over time as the more you design and the more you kind of build your own priors. And it could actually induce blind spots, though. I mean, you might make assumptions now much quicker than you have in the past that maybe a young guy coming in would kind of question and find new things. So there is an aspect there too that you always want to be somewhat open-minded as you navigate efficiently. Uh, and I think this is where we are today, where in conventional design, we have human designers really making the design moves throughout the design space. Um, Now, I didn't really wed this to an exact, let's say, design approach yet or methodology, but let's consider a couple of these and the available degrees of freedom. And yeah, throughout this talk, I'm talking about VLSI physical design, but I think a lot of these things can be expanded to various steps in the full front to back, let's say, chip design process, and maybe even beyond that more generally. But I have a target goal here to keep it somewhat on track. So uh, let's start with custom design, just kind of putting out a couple ends of the spectrum, an oldie but a goodie. Uh, this is what I learned to do when I was in school and when I first came to IBM, we were doing close to custom design. And if you're doing analog or non-standard digital without pre-characterized books or SRAM cells, you may be doing this now, and that's nothing wrong with that. When you don't have I would say the IP and the characterization, this is where you start. It also has a great deal of freedom. You have a blank canvas. You can do anything with your, say, layer palette. So you can, a key thing from a maybe framing it a little more digital throughout this talk, uh, you can size transistors exactly. You can lay out precise topologies. You can do this perfect. You have full freedom, but it's hugely expensive, a huge time commitment, and that's probably the key trade-off is full freedom versus I would say a high manual effort process. And you can automate it through some code, and it's still you still have to do a lot of uh, let's say human interaction work. And so that's kind of the key trade-off. Your analysis also is based on non-characterized uh, let's say, components as well. And so you're doing the more detailed, typically spice level. Hopefully, you have a transistor, let's say, cell that you don't have to go that deep, but that's kind of the idea. Is you're doing a highly manual process, highly expensive sign off. You're probably doing, let's say, detailed front end to back end line extraction, uh, and that's kind of the crux. Full freedom, except it just takes a long time and uh, I hopefully we can get things done faster. And fortunately we can. I mean, this is pretty standard too. The I'll call this either standard cell design, ASIC or SoC design throughout the talk. This is really the workhorse of digital design today. And I think the key thing that it leverages is abstraction. So the instances and the objects you're using in standard cell design or ASIC design, they have abstractions which give you the enough information that you need, but abstracts out all the details that you don't until you need them later. So that's the key thing. Now you can work a lot faster. You're not worried about you working at basically a higher level of abstraction. And then we have place and route tools that can, amazingly complete complex design. So these tools are highly sophisticated. They leverage the abstraction, and from a kind of a more simpler design, you can typically do with a one-line command at a text prompt. It would build the whole thing front to back. Uh, and then your sign-off is significantly faster too, as I mentioned. So typically you have pre-characterized, let's say, transistors and gates and front-end of line. So you're only doing in a back-end of line extraction. That's going to speed things up significantly. Uh, Now, one line command is good for, let's say, an easier design, but then the crux of it, okay, what do you do when that doesn't provide the quality you want? That's what we'll address. But the key thing is the build pipeline. You can go through a trial with very little human effort, still maybe a lot of compute time, perhaps, to do a full pass days to weeks, but at the same time, your effort is now significantly reduced. Uh, and there's a trade-off. I think we've learned to live with this trade-off, but yeah, if you're doing a highly detailed design, you may need to roll back to a custom view. So for example, tweaking transistor sizes, probably not possible within this space. Also, uh, libraries are typically characterized as specific voltage and process corner uh, bins, and you can add your own cells, but it's time consuming, it's painful, and you have to effectively characterize them to a similar quality as your other cells. So to that respect, though, these trade-offs, you lose a little bit of freedom. I would say it's worth it because of the efficiency. And that's where we are today. Now, I'll talk about something in between briefly. So uh, this is what I would call either standard cell design or semi-custom design. It's been around for a while. Uh, you know, high performance designs, we would do this, in the order of, 10, 15 years ago. Uh, and you may mix and match those two aspects. So standard cell libraries, but maybe a manual schematic entry or hand-coded netlist. Uh, and then you're going to do most of the work. But the key thing is you can express a lot of detail here, and it's a good trade-off. In IBM, we used a process like this until our automation became strong enough to do the high performance server products. So keep in mind this is something in between. So it really these methodologies are really a spectrum, is maybe the takeaway. Now where are we today? So this is what I would call closing the gap. And this is, again, I'm not maybe not saying anything new, but just to frame where I think we are today, is it's really the mixture of the concepts inspired by custom design merged with the efficiency of the ASIC flow. And so maybe two ways to look at this is some of these approaches are, I would say, more custom inspired in that, hey, I as a designer know what I want. I've done this before. I'm going to put surgical design moves in with hopefully minimal effort. And the idea would be almost see what the tool does. If you can do better, you have a better idea, then uh, effectively guide the tool based on your idea using some custom inspired approaches. At IBM, we used a term called structured synthesis techniques to kind of introduce as a sort of blending of our prior semi-custom approach with our more automated approach. And the idea is like, hey, so the things we can do in semi-custom design, we can then do them in the automated environment, just in a different way. And hopefully we won't have to do much. Leverage a tool and do surgical moves was the concept. And more broadly, the tools really just take a flow script. It's code, so you can do whatever you want. It's really an open-ended set of moves. If you think about it, you can modify the code in any way. And so with these aspects, we're basically having an automated process that with kind of a full expression palette to do whatever we want. And so it kind of looks like the following today. We, have humans sending in human designers sending in code into the tools, and then we can let the tool do the evaluation. We can tweak the code and iterate, and that's how we'll start exploring the design process. And so uh, maybe to get a little more concrete, I just want to blend these a little bit more, and I'll go through a quick number of examples of what I consider these custom inspired approaches. So let's kind of walk through. This is a sequence. Uh, Again, this is where a little bit of the older work comes in, but I think it's still relevant. I still use a lot of these techniques today uh, for various, when needed. And so this was based on some of the work when we were transitioning from a more, I would say, semi-custom approach into a automated approach. And again, a lot of these techniques are what kind of got us through that time period. And today, I still have a kind of a playbook of techniques that I would use depending on what I'm doing, and these are still in the playbook. So I would always try, again, I would call it more default synthesis to start. The idea there being that, hey, let's see what the tool does. But if the tool doesn't produce the result I want, one class of techniques is borrowing from what I would do as a designer. The other set of techniques I'll mention again are more automated flow script changes, but I'll walk through these to give you a sense of these techniques. And again, the reason why I'm doing these techniques is because the tool is not doing these the way I want. Now, hopefully the tools will advance and they'll keep on bringing in more sophistication. But today I can override the tool decision or guide the tool if I need to. So let's walk through these. So I'm going to use a mixture of IBM terms and industry terms. I think just the pictures will get the point across. So one thing we can do is to basically move bound or guide the instance placements. And this is a first order degree of complexity or human effort. Uh, let's say going from the bottom to the top. And I mention this more at the bottom is because this is a nice broad brush and I can grab a lot of objects by a regular expression, put them in a box, and that's all I have to do. I basically need the expression of the instances and the area where I want to put them, and that's all the effort I need to put in. And then I can guide the tool. So that's one nice approach. Next one. So I can also do this effectively with nets instead of instances. I can apply, let's say, various routing attributes, assign layers with spacings, and a number of other things, route priorities. That also is nice because I can use an expression to grab them and apply. This next technique, you could put this sort of in any order here. I kind of put it here because it's you do it early and it's touching lines of code, but you could recode the RTL to impose a structure. And that's a very useful technique to guide the tool. Getting more detail, instead of move bounding or guiding instant placement, I can actually place the exact instance exactly where I want. I could place it relative to another instance, but the key here is I'm having the granularity of actually placing a position versus a general region. Uh, you can also use an irregular expression of this, maybe grab a bunch of instances and put them down, maybe in a floral loop. But it is a more detailed technique. Then a more detailed routing technique, I can actually put down a shape instead of giving a guide or a attribute to the tool. Uh, Now, I have to do more here. I don't have to put the whole route in. So this is a spectrum too. I could put in a trunk route. I could put in a full route, but I am giving a more precise shape and placement to the shape. So more work. This next technique, I can actually modify the net list, put in buffering or whatever I want to do. I didn't have a great picture, great screenshot. So the concept is I put down a nice route here. This is maybe what I was doing before, kind of spaghetti route or squirreling around. I can kind of give that full structure if I want, but only if I need to. And then the following couple techniques, these are more, I would say, at the time of the IBM flow uh, paper, and they're still used today at IBM, and also they're kind of generalized too. But the idea is now we're playing with hierarchy. We might pre-synthesize some children blocks and then release the hierarchy or flatten them within the flow to have to break down the parent-child hierarchy boundaries. We might do more of a full, like schematic-based structure and then drop that in and flatten it. And then we could go to the point of embedding a complete hard IP, for example, like a customized cell. This is a lot of work. You have to characterize it, but it could have good payoff if you pick the right surgical cells to do. And then at the end of the spectrum, if you want to do the whole thing, you probably still could, but I don't want to do that. It's a lot of work. So the idea would be, hey, this is sort of a menu or playbook of techniques that you could use, and the design process is picking and choosing when to do this. And hopefully you would do as little as possible is the takeaway. Now, I'll go through a couple brief examples. I'm just going to show some pictures. These are the older pictures I mentioned, but they get the point across. So what we have here is by we're doing this multiplier component, conventional synthesis result, kind of again, see a Gates. If I impose some structure, maybe give it one embedded book or two embedded books, I get a significant improvement. You can scale this too. So this is a multiplier on the left I did, uh, pretty much in a semi-custom with some full custom components in there too. Many number of years ago when I first joined IBM, and it took, maybe a year. And then this is a nearly comparable version of it, which took maybe a couple weeks. And so in going through these designs myself, I kind of realized that, yeah, you can get high quality, but the pain and is maybe not worth it. So let's do something that is efficient. And furthermore, we get more, let's say, trial effort, and that I can try more experiments. I'm not locked into this, uh, you know, one design point for a long time. So that's an example. And then maybe moving to larger blocks, and these are even small by modern standards. Maybe these are 1/5 or 1/10 the size of the larger blocks that we'll do today. But uh, the example being is that at the time, these were pretty large units, which we could do effectively with all, synthesis, place, and route, which we couldn't in the past. And to get us over that to the automated process, we used a lot of these custom techniques. And then over time, the tool should improve. So hopefully, if we ever redid it, something like this, which we've moved on, we wouldn't have to do a lot of this. The tool is now innately smarter. But if it isn't, we still know how to close this. We still have the techniques to kind of bridge the gap. So that's maybe a run through techniques which I've found useful in a certain class, which I think are derived more from a prior design life, semi-custom approach. But more broadly, then I'll kind of sum it up in this section to say that I see this as a kind of a two regime interaction. There is a more of a closed loop regime of the CAD tool. It has a key thing there by closed move. I mean, it has a really a fixed set of moves it will do internally. It's not kind of making things up on the fly. It is a more, uh, again, fixed process. Whereas, today the human here is in an open move search process. Really can do whatever he or she wants, can invent new flow steps, invent new tool techniques, can send anything into the tool to see what happens for better or worse. And I think eventually we're in a process where these good moves ultimately make their way through, R&D at the CAD tool company into the tool. And then the tool is constantly giving feedback to the designer so that the tool itself is performing an evaluation, etc. So I'll start with this regime and then we'll kind of get more advanced as well. But let's take this as a starting point. Then maybe to summarize, this is standard practice. So I don't think I've said anything new, but yeah, the tool is the inner regime at this point. The engineer who invents things is the outer regime. And the designer's time is really uh, spent between kind of thinking of the design moves and then actually running the tools and reviewing the result and then coming up with the next design move. So that design process is really in the hands of the designer within this uh, framework. And then the full design time or schedule, it's really a summation of both. You have legit CAD tool run times. When you do a big run, it could take days to weeks. So it's non-trivial, but also the human is part of this too. The human is modifying, waiting for the run. The run doesn't start immediately. The human sleeps, the human, vacations and company interaction and stuff. So there is a lot of time there, and I don't have the exact percentages, but I would say they're both worth putting on the same set of bullet points here. And so uh, the goal then is how do we improve both of those? So there are ways. So let's start with one way, which is also kind of more of a standard. So I'll say enter the design flow tuner as one current approach, which is pretty, used in either, explicitly or in a sort of open loop process. This is sort of automating the types of things we may do as designers, but really, in my mind, it's tackling kind of the low-hanging fruit to start. And really what it's tackling is these CAD tool parameters, which is, again, really like a fixed space. Uh, and so that is a reasonable place to start. It makes a lot of sense because this is something that maps nicely to machine learning and maps nicely to, let's say, distributed computing. So we can throw compute at this problem, and it has a nice direct parallel to a lot of search processes like reinforcement learning or Bayesian optimization. These are kind of nice parameter tuning frameworks, and we have a kind of nice closed form parameter tuning problem. What it's not though is the what I was talking about in terms of what the open move set that maybe the designer is doing, kind of inventing new moves, uh, and it's not necessarily replacing the outer regime of the human, but it is taking a chunk of the human uh, work and making it a nice, uh, let's say, optimization problem. So I would say this is more of like a middle layer, and there's examples. So kind of more the uh, mainline CAD company examples from Synopsys, Cadence, and then we have our own tuner here at IBM. Synopsys, I'll talk about that because that was a project that I worked on here. So that's my insight here, and I'll give a little bit of a viewpoint on that. But let me kind of change our picture now. So we have a new picture with a design flow tuner in the middle here. And again, it's still, I would consider this a uh, closed move tuning system, but it does take a lot out of off the designer's plate, you could say. Yet the designer can still inject into this. So maybe the tuner isn't coming up with a new idea, but ultimately, it's all code. So the designer could inject a new piece of code, which is effectively a parameter which the tuner could take and then explore. And so the designer can now start to inject uh, ideas and open moves into this process, and then let the tuner interact with the CAD tool inner regime to figure out if it's a good move or not, or give it a, figure out, dial in exact numbers or settings. Let that detail, hand off that detail and let the human work a little bit at a higher level and really think about the key open moves. So if you're not familiar with design flow tuning, I'll walk you through from sort of a CAD tool to a tuner briefly. So we have a point CAD tool, and it takes typically a script, and it produces uh, data out. So data in, data out, point tool, logic synthesis is a good example. Uh, but that's one step in the pipeline or design flow. A full design flow is then going to be a set of steps, and it doesn't have to be these exact 6 steps, but usually it's sort of like these where we have logic synthesis, floor planning, placement, clock tree synthesis, routing, sign off. This is a kind of a linear progression example. You could make this in many ways. You can add steps, remove steps. You could loop steps for optimization passes, but thinking this, now you can think of a more solidified higher level abstraction as a tool flow pipeline. And then if we want to run it as a design flow tuner, the idea is that we have the ability then to uh, submit multiple parallel and iterative passes of this design flow pipeline. We don't necessarily have to run all the steps either. That's a key thing, is we can run a partial set of this pipeline at different trials or scenarios to get the information we want. It could be a nice trade-off between runtime and QOR, or let's say metric accuracy. But the idea is now we're working at the pipeline level of granularity, and we're putting a system around it to manipulate that pipeline. So hopefully design flow tuning makes sense. I'll show a couple examples then of the systems I worked on and just give the basic flavor. I'm not trying to go into too much detail here. I want to make sure we hit the new things at the end. So this is the IBM STS and TuneSys system. I think the key takeaways is that implement an online and offline learning system with also the ability for the expert to inject, let's say, parameters to tune. And so it was trying to do a lot of things. Uh, and this is kind of a concept system. We did use it on, particularly the online system, on most IBM server chips since 2012. So highly, I would say, practical, but also a good, I would say, research bed to develop the interaction, because we do have systems like online, offline interacting, and that interaction complexity is uh, the interesting part, I think. But so we did have a way to explore this. Uh, just another view of this, of more schematically. So the idea would be we would have like a library of primitives or moves, and then we would have a process that generates parallel scenarios. It would run synthesis. And when I say synthesis, this is actually synthesis in partial place and route. The step is kind of configurable. I think the takeaway is it's like a parallel and iterative search process. And I think that's kind of the key thing, simply because the number of possibilities, I mean, you can't do it in one shot parallelized, and you can't wait for multiple iterations. So you have a couple iterations, maybe 4 to 5 iterations in practice to get a good result. And you're really looking for a good enough result based on a multi, let's say, parameter uh, you know, cost function. The other thing is we would archive the results, and then that would kind of allow an offline process to also send in recommendations. So just the takeaway is these tuning systems can be complex. There can be online and offline components, and how you mix them together is really the uh, kind of the sauce that kind of gets these two things working differently. So this is the system I worked on. I'll even say modern tuners, Synopsys, Cadence, the big CAD companies, they are doing a great job here. So want to make sure people are aware that these are kind of the modern day offerings. Uh, I did have a table here to kind of compare. I'm not saying that any judgment here. This was AI generated, so I just citing the sources that it gave me here. But the idea would be, uh, this is in practice, so I would say that this could be phased into a, real world design flow and should be considered now a solidified part of the design process. So I also mentioned if you're not as familiar with design flow tuning, we have tuners that span or let's say research has been spanned across multiple topics. So HLS, logic synthesis, physical design is where I work, and then FPGAs, all tuning, various parameters. Although I would say the uh, logic synthesis and physical design, well, I mean, you can see the parameter count can explode in comparison to since there's a multi-step pipeline. Uh, Now, so this is kind of the background if you're interested in working in these other fields. But let's get into what even a parameter is and try to step away from that open, or sorry, that closed move regime and think about what an open move tuning system would do. And we can kind of walk through the parameter space. So we have a CAD tool parameter. We have flow script parameters. These are perhaps parameters in the flow script itself that aren't within the CAD tool. And then we have the ability to hit semi-custom and open-ended moves really everywhere. And then the tuner itself is actually a parameterized system typically. You have hyperparameters that hit, let's say, the number of iterations, the number of parallel runs. And so I think this is where we get the parameter explosion coming in. But I think there's practical ways to ease these in, I was just describing, to let the system slowly evolve and take in parameters, as I'll describe in the next few slides. So I can think of at least two strategies. A strategy A, which is more of a, let's say, a knowledge capture, somewhat similar to the offline approach and the human approach I've been describing in the prior Sentunsa system. So that's more of a, let's say, maybe a known strategy. But also, I think there's a definite opportunity for agents here in LLM. So that's more of a generative strategy, generating and trial and error these approaches. I think these two strategies, while they're somewhat different in, let's say, maybe the way they're developed, they can actually work together too. And so maybe a next level improvement to try to automate the outer regime would be uh, trying multiple approaches and then having a way to, this is more of like a sort of like a training process here where we're evaluating moves, and then eventually moves get uh, promoted into, let's say, the tuning parameter set. So a lot of ways you could do this, but this is kind of one approach. It sort of eases our way there and allows a, say, gradual improvement. So I'll mention this briefly, but hierarchical design is another task, which if I didn't mention this, I would have felt bad that I did not mention a key challenge is we're doing this so far in context to a single context or design macro. In practice, we have multiple levels of hierarchy, many macros in a complex chip design, and we really have to come up with a strategy to handle them all. Uh, I'll kind of leave it at that for brevity, but the key takeaway is that we can think about the macros in their own context, but we will have to eventually roll this up through the hierarchy. Now, this is also a clear uh, scope of the human today. I don't think there's fundamental barriers why, though. It's a more of a bookkeeping and synchronization problem. It is you could say if we're doing tuning all the children having, let's say this process roll up, it is also a very compute intensive problem too. So there are trade-offs in that we probably can't apply the same effort to every design. Is a choice. And that's sort of a concept I was putting together here early, how to trade off the, let's say, tuning perspective ROI, or uh, let's say, what macros do you tune at what priority, and how do you kind of roll them all up together? Then it looks like there are new products coming out that do address this from a more proper EDA vendor perspective that you could pull into your design flow today. So just mentioning a brief side of hierarchy. Now, my last few minutes, I'm going to mention some problems which I think are beyond tuning. They're more like let's say, parallel problems. Uh, but these are problems that perhaps are not as obvious and maybe keep me up at night more from a manager hat on here, that, hey, these are things that if they don't turn out, we are in trouble. So I want to mention these and think, kind of maybe brainstorm about what automation we could do here. So one aspect is really the design environment setup. This is a square in the domain of a human today. Uh, and why it's important is because it is kind of treated as a trusted oracle for all the tuning processes and all the design work. We kind of assume our setup numbers are correct, but that could be quite wrong. If your design environment is not set up correctly, everything you're doing is effectively uh, you know, evaluating against a wrong oracle. And silence or failures are sign that you might not see the result until it's too late. One example is the timing environment. It can be quite complex. So if you are familiar with the timing constraints or the SDCs, these could come from multiple teams. And multiple teams usually have different perspectives. And when you actually build a design, you are kind of taking uh, multiple perspectives and trying to merge it into a single view that actually, is consistent with the design we're building. So that's challenging. Also, the technology is sending in information to tune the sign-off settings for their particular uh, fab. So all these things together is a highly manual process. But I'm hoping then automation can uh, reduce the risk. I'm hoping it can minimize the uh, overhead and cost to do it. But it's also a thing that we don't want to kind of let go fully until we're highly confident that an automation or process or an agent could do this well. And there's various other checks. So every sign-off check, I mean, this is kind of the ground truth. These have to be right for the chip to go out if we want it to operate correctly. So any kind of setup here is a high risk, but also a clear overhead and human task. And so a couple thoughts. I mean, having these stronger verification chains could be an angle here. For example, an SDC, can we have sort of some chain that reflects the intent rather than just trying to have it, so fully separated from the purpose, just a number. And another thought is maybe agents can help us here, but we still have an approval process that, again, I would not risk a multi-million-dollar tape out on a recommended, uh, let's say, setting. Even if it seems like, oh, it's going to save a lot of time, I still want to be sure. Maybe, until you're highly convinced that this thing is working as appropriate. I think the concept of a propose and approval uh, makes a lot of sense. All right, putting this into a picture, I got a couple more slides, so then we'll move to questions. Uh, this does kind of bring in the concept that, okay, now we have multiple, somewhat separate groups, even potentially from different companies, sending an input to this environment. This is then driving the evaluation function, uh, which is effectively the evaluation for all the regimes for tuning we've been talking about. Now, here's a couple ways that we can improve this. So the thought of, again, the concept of creating better chains of, let's say, from RTL to the actual, let's say, SDCs. That's one process. We have, things where we can determine, hey, can we prove based on the RTL settings? We have multiple linting processes. So I think this is an approach that really just kind of puts together a more detailed chain and also enhances looking for errors and spotting errors. So it's maybe not too wildly crazy here, but I do think adding this structure and strictness can help. Another quick one is waiver judgment. The idea there is that humans make decisions to bypass sign-off checks or waive small violations in many cases to improve the schedule. And so this is key. In doing so, we're actually reducing the amount of work, but it's really key that it's a correct call. But this will happen in nearly every project, and it will improve the schedule. So how can we handle this? This is clearly yet another human in the loop domain. But yeah, I do think that probably a similar approach where agents can more propose with humans still verifying until certain waivers are perhaps then granted autonomy through proper track records. But yeah, throwing out the waiver judgment is another domain. And maybe one final domain here is the intercompany communication. So you can do all this right if you can't get your IP or you have uh, let's say, a missing detail in the IP, it's still not going to work. And this may be one of the most complex problems. The macros that often we worry about the most are these complex macros that consist of external IP integrated with in-house logic and DFT. So we're bringing together components from multiple groups, different organizations, and um, you know, nobody really has the full picture, and it's left to the design team to complete the full picture with a lot of components that they haven't really uh, internally generated. And so that is a challenge. I do think perhaps improve linting, and then I think LMs could be kind of a conflict detection. So if multiple groups are saying different things, can we have a clear, let's say, conflict detection could be one way. So these are the things that sort of keep me up at night. Maybe not standard optimization problems, but I do kind of have eyes on these and, how can we improve them? And with that, I think I'm just out of time here. I'll wrap up. I'll give my closing remarks. And if you remember back at the beginning, I was trying to convince everybody here that VLSI design is search. Uh, and then a lot of the human guided ASIC uh, approaches, again, I was saying these are kind of originating from a lot of earlier EDA flows. And really today, we're working in a kind of a tuning environment, which is still a closed move regime. But the hope is that we can break down these bottlenecks and move into a uh, open move regime in the future. And finally, we'll have other human in loops, as I mentioned, the kind of environment sign-off set, waiver judgment, uh, cross company. These are kind of non-standard things which are may become bottlenecks. These may be human tasks for a while, but I would also like to try see if we can improve these because there's a lot of risk in here and also a lot of effort. And then I still have general challenges and concerns. There is a pure runtime problem to this entire prospect. Uh, our largest designs take weeks. The number of trials and compute that we have is limited. How do we get these results better? I mentioned hierarchical design. That's a complexity problem of its own. And then, yeah, the complex macros that span, let's say, IP and multiple companies and departments, those are always challenging because we really uh, never have a great, let's say, full view of the problem, and there's risk there. And so hopefully automation can help all of these topics. And with that, I'll conclude. I thank you for my time. If we have questions, I can go with those as well.
Thank you, Matt, so much for the brilliant talk. And right now, Matt, could you see the Q&A panel? There are some questions there.
Yeah, I can.
Yeah, could you repeat the question and then briefly
Yes, okay,
share
great.
your
I'll
opinion?
jump back to the slide 35 that was mentioned. get this up here. Okay, I think, is this the slide? Yeah, so the question was DTCO, how does your LSPD workflow facilitate DTCO, so design technology co-optimization? Yeah, I think it can, absolutely. So, and there's been papers published on this from multiple companies and groups. I think the idea is that the, let's say the options and parameters within the technology space, they simply manifest themselves as tuning parameters. And then, so whereas typically you're tuning a design based on, let's say, CAD tool parameters or other flow script parameters, you could imagine components of the PDK, maybe the track cell spacing or the, uh, let's say, various metal widths or whatever with your technology. If you can parameterize it and you can modify the flow script to the tool, you can tune it. And so I think that's very practical, and I think I'm certainly sure most technology companies are doing that. Okay. Oh, I think I know Linda. So the question is, what complexities are you seeing with the shift of earlier emulation and impacts on design flow to the schedule? So yeah, I think that's a front end problem mostly. Uh, Let me just double check this. Yeah, so I think in a way, I mean, sounds like it's more of a shift left approach. Yeah, the more we can do early, the more the better. Maybe that's can we, you know, I think a lot of this can roll into uh, early analysis, the same concepts of if there is a design space, can we uh, uh, search it? Can we search it effectively? Can we look for early problems? I think it translates, is maybe my quick uh, okay, this is a fine question too. And so the next question is intent linked authoring. Why are free text comments ignored? I don't think that maybe that's a too harsh of a statement. I think free text comments are, with a, let's say, a tool like let's say LM that can understand text. I think that's valid. And maybe it's more trying to improve the conciseness through a more structured approach. But I could see if you already, it probably is additional help or just additional information. So my first response would be um, if it's kind of interpreted correctly by the let's say the tool and can be used constructively, it's probably more information is better. Um, but I think the thought would be, hey, is there more of a structured way to do this up front? And a couple more questions. I see two more. Hopefully we're still on time. I'll go if no, we're at the hour, but I'll hit these last two. So the next question is, if processor architects and IC designers favor coarse grain configurable architecture, can we speed up physical design from days to weeks to less than a day? So coarse grain, and so in some way, I think I get the thought here. I mean, I still think then if you're talking coarse grain, let's get the exact definition. Uh, I mean, if we're I would say an architectural level coarse grain, I mean, perhaps if you have a way in which you're not having to implement you kind of have pre-implemented functions in which you can uh, switch between. I mean, that could be maybe if you have if you can improve reuse through physical design. I mean, the cost is building everything from scratch is expensive. If you have kind of coarse grain components which you can reuse, there's been many projects on that. That does make a lot of sense. There is a time to market, I would say, a compelling case for improving reuse, perhaps at a, having coarser grain components rather than fine grain, let's say RTL level implementation. I hope that hits the spirit of the question. And okay, three questions from the same person, but I'll hit them all. Okay, so the question is, the questioner states, I have experience in embedded systems and FPGA. He wants to transition to ASIC and VLSI design. Which skills should I prioritize the next 12 months to become industry ready? So I think probably you have a lot of from a embedded systems front end. I think obviously what's fairly common is the front end. So let's say the RTL, the simulation, that is a common, you can take a piece of RTL and you can send it almost in this exact picture through FPGA or let's say ASIC flows. So that part's probably, you probably have that. Then, yeah, I think where the difference diverges is from the uh, what you do with how do you implement or realize the RTL on hardware. So I guess my simple question is, or my simple response is, I probably would start to work through the pipeline, uh, really at the starting point. And, for example, uh, the simplest thing, these steps are going to get progressively more complicated. Uh, and I wouldn't necessarily focus on one, but I would probably actually take an example flow script, take a class or example flow script, and take a piece of RTL and actually implement it. Focus on logic synthesis. That's going to be fast. That's going to be the aspect which, let's say once you learn how the CAD tools behave and sort of the flavor, that's a fast turnaround and learning process. And then in parallel, I mean, I'd be doing two things. I'd be reading, I'd be watching videos, and I'd be exercising with hands-on, building anything. Uh, and yeah, you could get through it in 12 months. It would take a lifetime to be an expert, and I'll never be the expert I want to be. So I would just kind of, combine both a hands-on and a practical uh, going through actual tools. And then actually there is, I would say, a set of learning you can do in parallel. So I usually, when students take my class, I would say, hey, I'm going to assume you know this, but if you don't, here's a couple websites, which I think is great material. Learn that and then learn the hands-on. Sorry if that's a long response. Now, the second question is open source tools like OpenRoad, OpenLane, Magic. Yeah, I think, the question is, do those provide practical experience for someone preparing for industry? I think so, in that tools will be different, syntax will be different, but it's more of the concept and uh, you know, I would say the experience. So gaining experience any way you can, I think is the valuable thing. I mentioned the intuition that doesn't, I don't have a perfect way to convey that. If I did, we'd tell it to the tool. So you do have to go through the experience. Uh, Now, it does get more complicated at advanced nodes, advanced tools, but you have to learn someplace, and the tool you learn on maybe isn't the tool you are using at various points in your career. So I actually think it's not a bad thing to get, let's say, a view of all the different tool types, the tool companies. You'll make connections, you'll learn more. And it's like a programming language in the end. I mean, uh, the exact language is maybe not what we want in skilled programmers. It's the concepts, and I think they'll translate across tools. Okay, still coming in. I'm happy to take all these. So with an increasing automating physical design tasks, which skills will remain uniquely valuable for engineers within the next 5 to 10 years? That's true. Yeah, as I was trying to present, I would anticipate and hope and look forward to, again, the automation doing more, making us as designers more powerful. So I would say that I would look at what are the, you know, the kind of core design things we're trying to do. Or now there's two views. One is we will move kind of at a higher level, as I kind of described, kind of moving up through these regimes. And so I would say knowing the design moves is kind of still important until we're fully automated. If we're looking at a single context design, uh, like macro, knowing what to do is still important. Uh, and then you'll probably be able to do more with less effort sending it into the tool. And the other view is there are a number of kind of topics which are more squarely in the human domain. These are the ones I listed at the end, kind of like the, again, the environment setups, dealing with complex problems and cross company, like taking, again, setting up an STC when you're kind of having information coming from logic, DFT, and then uh, having to mix all that together, uh, you know, that actually is complicated. So I would say certainly go into the more, you know, human aspects too, not human aspects, but human dominated areas. I think they'll kind of be the last thing standing for humans potentially. But so I would say think about that. So yeah, know what you want to do. More try to guide that intuition, and then also let's keep an eye on the problems that are still hard for these tools. Okay, I think we have two more. So the next one is for someone interested in AI acceleration and RISC-V SoC design, what kind of personal projects would make a candidate stand out for roles at IBM? Yeah, that's great. So uh, I do think a lot of this, uh, with the interest in this area, it's a great area to get into. Um, a lot of there are, by definition, some open source thing with RISC-V. There's open source. I think you can start to explore this, perhaps, uh, you know, through open source. If you do have access to then industry tools, that comparison. Uh, but I do think, what kind of makes me interested is, have you gone through the the process? Have you felt the pain? Like there's no way around I would say the design experience. And so, yeah, even starting to assume that, okay, the first step is to actually build something that, there's a cutoff point. You might not have to fab it and you probably won't unless you have a budget and a need. There's no need to make something that we're not really going to use. But to go through the process, I think is kind of the key thing. And then think about and say, how can we do this better? How can you start to build up the intuition? Uh, so, and it depends what you're trying to do. If you want, if you're targeting a specific goal, I want, let's say, the AI accelerator to do this or the RISC-V do that, then think about how you would modify the RTL uh, and how you would adapt it. That's I think, the beauty of open source. The other aspect is if you're interested in then how do you optimize it or implement it from physical design, then somewhat having a fixed RTL that is of reasonable complexity, maybe not too simple, not too complex, and then going through the process, kind of seeing the metrics, and then trying to make it better. And so you are sort of actually being the tuner is very instructive when you start out because you're having to make the decisions that prior designers had to make, and maybe some of it will be automated, but I think one thing that we risk in terms of kind of moving always to a higher level is that, yeah, how are we going to learn these prior instincts? And so, yeah, going through the process and iterating is maybe my best advice. And then, yeah, showing, okay, these are how the metrics improved. I reduced power this way. I, ultimately achieved this through let's say practice. And then the final question, if you were mentoring a motivated engineer who is learning independently, what would the first three practical projects you would recommend? Okay, it really depends what you're motivated to do in your career. Uh, so I'll take a simple first one would be, and maybe trying to maybe go along the lines of the talk. I would probably pick something that you are interested in, maybe the AI Accelerator or RISC-V component, take something like that and then try to understand it, and then also implement it, and then perhaps uh, you know, so that's a good starter project. Learn that. And then, if we want to really tie it back to this talk, I would then start to think about how you can make it better kind of through the design moves. Maybe another one would be start to write a tuner yourself. So see, can you start to automate your design process? Uh, and again, that's a lofty goal, but start to think critically about why you do the design moves you do and how to make it efficient. So that would be another project. And then perhaps three practical projects. For a third one, yeah, I also can, maybe I'll even give a couple different deviations on it. So another one might be typically in this flow process, we kind of just go through the place and route tool and we kind of look at the results there. I would kind of look at maybe two things. One would be the complexity of the sign off. How do you actually prove that the results are what they are? Another might be uh, phase in some hierarchical design. That's kind of a key skill that's not as taught as often. So I don't know if your example project if you were working on the first one, if it required hierarchy, probably it didn't. But I might force some hierarchy in here to make you think about how, let's say, a larger chip would work. And so it's almost impractical for a large chip, uh, a large, let's say, SoC or AI processor. You're going to have a single flat hierarchy. You're going to have many blocks interacting, multiple levels of hierarchy. So to emulate in ways might be a good thing. So you would have then let's say, a starter block. You could optimize. You could start to kind of write a tuner, maybe then force some hierarchy in there to get a chip level understanding. All right. Hopefully that hit all the questions. Happy to, if you want to hit me up with more, my email should be available. Feel free. Uh, and with that, yeah, thanks. It was kind of fun to share some perspective here. Appreciate the attendance.
Thank you for your insights and your brilliant talk, Matt. And thank you everyone for participating in this talk. And thank you for CASS Society to support this webinar.
All right. Take care. Have a great day, everyone.
Have a good day. Bye.